Let X be a delta complex. Then first let delta n x be the so here we are not considering orientation, right? So in the previous case, when we were considering simplicial complexes, then this CQK, when we were talking about this, we are considering this to be a abelian group generated by oriented Q simplices with the relation sigma 1 Q plus sigma 2 Q equal to 0, where sigma 1 Q and sigma 2 Q are oriented Q simplices corresponding to the same simplex. So here we are not considering orientation. So let this be the so in the generator set, basically what does it mean? Here also means both the things are, there is not much difference. So here basically generator set is the set of Q simplices here. And here also. So let this be the free abelian group. Free abelian group generated by the open n simplices or the basis the open n simplices En alpha of x. So what is this En alpha basically? This En alpha is basically sigma alpha applied over this interior, right? What is this? So these ones we call open n simplices of x. So they are basically subsets of x. They are portions of x. So delta nx is generated by open n simplices E alpha n, and elements of are called these are called n chains. And can be written as finite formal sums. Alpha sigma this is En alpha. So this is finite sum, right? So where alpha, this is in Z, coefficients are in Z. Next, this sigma alpha, this can be thought of as n chain alpha alpha alpha. So why we are able to do something like, why we are able to say something like this? You just see that for every sigma alpha n, there is a open right, open n simplex, this, right? And for every open n simplex, there is, so there is one correspondence, right? So for every open n simplex, this of x corresponds to a map of this kind, right? This is a map, this alpha n, this is a map from delta n to x. Okay, this alpha. Okay, so if this is there, then this is there. If this is there, then this is there. So you see, how to differentiate two things? Uh, Two things you can differentiate only when one is at some point one is present and other is not present, and some other point other is present and first one is not present. But if at each point where one is present, other one also is present, you cannot differentiate them, right? So you can, in fact, identify these two, right? You can say that these two are same, but though they are not same actually. They are. This is a chain consisting of maps. This is a chain consisting of some subsets of X. uh, so, but both the things are different, but you can identify them with each other. Now, next we define boundary map from this to this by so so we are, because these are generated by uh, these, so we are supposed to define boundary map over this, but because we are identifying this right? uh, so we can define it over this itself, right? So what we can do, that let us define it like this. This is equal to I to the power I Uh, so this one, we consider this one alpha n to be mapped from delta n to x. Okay. So this uh, uh, we can define it like this: sigma alpha restricted over I v n. So here this delta n is, we are considering it to be this applied over uh, n minus 1 into this. So we can define something like this. Now we have following lemma. Lemma is composition this are from the nx to minus 1x and from to x. This is 0, right? This is 0, right? So we'll see proof is similar to the case when we are discussing the homology of simplicial complexes. So proof simple can be equal to, by definition, I equal to 0 to n minus 1 to the power I n minus 1 sigma n alpha restricted over not I n delta n minus 1 is this again. We apply this over these. So this will be some open and simplex. Right? This is going to be j less than I summation I equal to 0 to n minus 1 to the power I minus 1 to the power j sigma n alpha restricted over E naught Bj cap Bi cap n delta 2 plus.
Okay, ma'am, we will be doing it, ma'am. We are not doing it, ma'am. This is going side, this going side. No, it's very considering this situation, no, ma'am. So whatever, no addition is there, no addition, no addition. You have to take it. They are taking it out. Yes, sir. Yes, ma'am. What about record? They are recording, so they have removed from my room. Okay. And they will put it there. Okay. So you can remove, means my everything. Only that for that, and everything is. All right. Okay. Now only take a minute.
This. So using similar argument as before, this is going to be 0. So you can change here role of I and j, then we have 0. Next, we discuss some examples that we compute homology group of some spaces. Examples. So first example, yeah, just before we start this, because this is a boundary map, right? Because it satisfies this condition, it's equal to 0. So it gives a homomorphism from delta nx to delta n minus 1 x, right? With this condition, this delta nx, this is a chain complex, right? Homology business of this chain complex, which is Hn x, will be defined as Z n delta x represented by B n delta x. Right, and this is called simplicial homology. Right? Simplicial homology of simplicial homology of delta complex x. So now we come to examples. First example that we will take, that of circle x circle. So first we have to find a delta complex structure. So we will put simplest one, right? That is with So you have one 0 uh, shell and one shell. So this is, so this keeps a data complex structure, right? So this is basically what you can say. This is E is what here, E is your E uh, 1, right? Uh, right here, this V is your E0, right? 0 open simplex. 0 means this is open simplex of dimension 0. Now, so you can see that delta 1 x, that is this. So how many one open one simplices are there? Only one, this one. So this is basically Z. It generates free abelian group generated by single element, just Z. And this one is Z. This. Okay. Now n s1 0, because there are no for n greater than equal to 2, for there are no open n simplices of dimension greater than equal to 2. So this now this one is what? So we use definition. So if we have some simply this cell P0 P1, then the boundary map this comes out to be so if you recall the definition, then you remove -1 to the power 0, right? And then you consider uh, uh, you remove V0 and then you restrict the uh, sigma alpha over this V1. So, so you will get actually in this case, let us write here. So this we can just write it. This is just a simplex, right? So in the case of simplicial complexes, we read this. So this is -1 to the power 0, simply V1 plus -1 to the power 1, simply V0, right? So this is, so V0 cap B1 means just B1. B0 comma B1 cap means just this. This is what? This plus V1, so this is V1 minus V0. So because we are considering, in that case, we considered oriented simplices, so we have something like this. Uh, but here we are not considering oriented simplices, so this is going to be minus 1 to the power 0 sigma 1 restricted over. So this open one simplex will be image of delta naught, right? So you can and this one you may consider yes, yes. So this is from V1, okay, right over delta 0 plus minus 1 to the power 1 sigma 1 over this 1 and this when you restrict, so this one this is, if you consider this uh, delta standard one simplex, then this v naught and v1 both go to v, right? So if you restrict this sigma 1 over just v1, right, then you will get again this v, and here again v naught and v1 both go to v. So here this minus v 0. Or simple method if you want to use, then if you want to use simple method, then v1, then this sigma applied over v naught e1, you can just write v1 minus v naught. Similarly, if you have two simplex v2, then sigma applied over v naught v1 v2, then this is your v naught you remove, then you have v1 v2, then v1 you remove with minus 1 to the power 1 sign, then minus v naught v2, then this you remove, then you have plus v naught v1, right? So this is this. Now so what will be the Z one S1 by B1 S1, but there are no what is this Bn x is what this is n plus 1 image of this image of n plus 1, but there are no two-dimensional simplices. I think it will stop. So we will stop and start again and complete it. So in the first example, what we have delta 1 S1 right is Z delta naught only one 0 simplex This is again Z, and delta n s1 equal to 0 for n greater than equal to 2. Now this one E C E, right, one cell and one. So this is just V minus V 0, because we have seen that we are just we calculate this V naught V1. This is just V1 minus V naught. So this bracket I am not putting here because that was for the case when we are considering oriented simplices, but here we are not considering oriented simplices. This because this bracket was there because it represented a class, right? Class. So this so it means kernel 1 the Z1 S1 equal to simply Z, because yeah, so kernel is generated by this E, right? And uh, all these are 0, right? And of course uh, this also is 0. Okay. So first 0th homology group, this equal to basically it is basically kernel of this is basically delta 1 quotiented by uh, 1 this, but because boundary map, it takes everything to 0, right? So delta 1 s1 is generated by this E, and E goes to 0 by this boundary map. It means that whole this goes to 0. So this image, this is 0 trivial. So this is basically, and this is Z, so this is basically Z. H1 S1, this is Z1 S1 quotiented by B2 S1. This is B2 S1 is image of sorry, B1 S1. So B1 S1 is B1 S1 is image of this map. But there is no zero, no two cells, right? There are no two cells are two-dimensional simplices. So this is 0. Or you can say that delta 2 is 0. So this is 0. So this Z1 S1 is Z. So this again becomes Z. And H2 S1 is 0. In fact, HN SN S1 is 0 for every equal to 2, uh, because this because of this, right? So we have computed the homology group of in fact simplicial homology group. It will turn out to be a homology group, right? Better as 0th homology group of S1 is Z, first homology group of S1 is Z, and nth homology group of S1 for n greater than equal to 2 is trivial. Next, We compute homology group of torus. So X is torus. Torus, we know it can be made by identifying these opposite edges like this. This you identify this with this with this, right? So this is A, B, B. So this gives a torus. Now we want a delta complex structure over this. So for that, we'll just consider C. Okay. So this is L and this. So basically these they will be identified in torus. So this is basically same vertex. So we have how many one cells? These two are one, and then two, then three. So three one cells, right? Are three one-dimensional open simplices, two cells, and one zero cell. So this is delta 0 T is Z, because there is only one zero dimensional open simplex. Right, it is span of V, right? What is delta 1T? So how many? 1, 2, 3. So Z plus Z plus Z, span of A, B, C. 2T equal to Z plus Z, span of and L. These two open simplices of dimension 2, and delta NT equal to 0 or n greater than equal to 3. This. So now we see what are the boundary maps. To U, so we have to choose some kind of some orientation we have to choose, right? So suppose we choose an orientation in this direction, then and here we can choose an orientation in this direction. And some representative we have to take, right? So here if we choose this, then this is going to be if you remove this, then if you remove this one, then this, so minus E, and if you remove this one, then this B, but here this will be with minus sign, minus b. So same way, like if you apply boundary map, so because these three vertices are same, if we would have v naught, v1, v2, then v naught, v1, v2, this if you apply boundary map over this, then we have what? V naught when you remove, then minus 1 to the power 0, so this is v1, v2, plus minus 1 to the power 1, you remove v1, so this is minus v naught, v2, minus, minus, and then minus 1 to the power 2, you remove v2, so here v naught, v1, right? So first you have v1, v2, right? v1 is this, v2 is this, so this one, but this is in the opposite direction of a, right? So minus a. Now v naught, v2, v naught is this, v2 is this, so v naught, v2, like in this direction with minus sign, right? So minus, and v naught, v2 is in direction of v, so I have written minus b, minus v naught, v2, and v naught, v1, v naught, v1, it is in the direction of c. So we have to choose some representative we have to choose. So once you choose some representative, it will have some, it will represent some orientation, right? So because of this adding, the way we have put it. Then this one, when you apply boundary map over this one, L, then we have here again this. So you remove this one here, then you have this B, and then if you remove this one, then you have this, that is C, but with minus sign. Now if you remove this one, then you have this, that is A, this plus sign. So basically you have A plus B minus C, right? But this is what? This is nothing but minus of okay. It means what? So these both the one generator goes to this, other generator goes to minus of this. It means image, hence image B1 T equal to image 2 equal to Z, and this is span of A plus B minus C. You can see, right? Whether you say span of this or span of this, whatever. Now what is kernel of boundary this map? So to AU plus BL, right? So a general element in this will be of the for this AU plus BL, because this is generated by this U and L. So this if we apply and it is 0 implies we want to find elements of kernel. So this is A times u goes to minus a minus b plus c plus b times L goes to b minus c plus e 0, which implies that a minus, this you can write as uh, b minus a plus b minus c. A and b we have already used, so we have to use something else. Yes, we cannot use a and b. So maybe p and q we can use. P here, q here. So q minus p, this equal to 0. So this is 0 implies p equal to q, right? Because this is not 0, of course. A plus b minus c is not 0. So this will have to be 0. Uh, so So what will be the kernel? Hence, uh, T equal to kernel equal to uh, so if this is 0, it means P and Q will be equal, right? So that is these kind of elements. Only these kind of elements will be in the kernel. That is but they will be generated by U plus L, right? It means span of U plus L. But what is this? This is Z. Now, spine of, because see, this is 0, boundary 4, boundary of this 4, this is 0, and so on. So this second homology group is T quotiented by B to T, but B to T is image of bound this, but this is 0, so this is basically Z. Okay, and now B1T comes out to be this. So B1T comes out to be this. And what is uh, so B1T is this. And what is Z1T? Z1T, let us see. So B1T comes out to be Z generated by A plus B minus C. Now, if you apply this over A, because both the vertices are B, right, of A, B, and C, so this is B, C, 0, right? So kernel Z1T equal to kernel this is what. It is generated by A, B, and C, both, all the three. It is Z plus Z, and it is generated by span of A, B, and C. But we can consider it to be span of A, B, and A, B minus C. Right? So A, B, and A, B minus C. This we can write span of A, comma B, comma A plus B minus C. Because these three will give minus C, and then minus C, from minus C we can get C. So this. Now what is the first homology group? This is Z1T quotiented by B1T. But Z1T is what? It is this spanned by this, and your B1T is Z, and it is spanned by this. So when you quotient it, uh, this will cancel, and then we'll have and because image of equal to 0, right? Hence equal to represented by Z, because delta not T, this is Z, and this B H N H and T equal to nth homology group. This is equal to 0 if n is greater than or equal to 3, because this 0 if n is greater than or equal to 3.